Assalamualaikum warahmatullahi wabarakatuh. So for this lecture I'll talk about stratification and adjustment. So objective of the lecture includes number one, to understand stratification and bias, right? And number two, to be able to identify stratification bias. To understand, number one, you must be able to understand it. You must be able to identify stratification and bias in study. And how will you use stratification and bias in studies? I'm sorry, how will you use stratification to control for bias in EPID study? All right. Use stratification to control bias. All right. Most of the contents of the lecture come from chapter 7 from this book, Epidemiology Beyond the Basics, 4th edition by Sisklo and also Nito. So next, right, introduction. Stratification and multivariate analysis modeling are analytical tools used to control for confounding effects. Number one. Number two, to assess for effect modification. And number three, to summarize the associations of several predictors or independent variables or covariates with disease risk in an efficient fashion. The simplest method to analyze possible presence of confounding is stratification. Right? So it is very informative because it allows a straightforward and simultaneous examinations of possible presence of both confounding and effect modification. So you can test both, one confounding and number two effect modification. Examining stratified result also useful because it is one way of choosing the appropriate statistical technique for adjustment. That is stratification. Next is multivariate analysis, a series of analytical techniques. Could be a less complicated or complex mathematical modeling with the aim to carry out statistical adjustment. Okay, that is what we are interested to do, is to do estimation of association between an exposure or independent variable and outcome or dependent variable while controlling for one or more confounding variables. So this is stratification and this is multivariate analysis. So both stratification and adjustment can disentangle confounding. Right? So for example, in table 7.1, right, in this table, so you look at the odds ratio here, right, and this one for all cases, this one stratification outdoor occupation and indoor occupation. This study would like actually examine the relationship between sex and being infected with malaria. So the odds ratio of 1.71 tells us that there is association between sex and malaria infection, right? So let's go and see the caption. So this is a hypothetical example, a case control study. Male gender as a possible risk factor. Male gender is a possible risk factor, okay, for malaria infection. So the crew analysis suggests that males are at higher risk of malaria, odds ratio of 1.71. So males have like 71% higher risk for malaria compared to females. Right? Systematic errors seems to be unlikely based on this example. So next, what we need to do is to look for possibility of confounding. Right? So is it really because of the sex or because of other things like occupation? Okay. Because males go out and females stay home in this area. So is that one of the reason? Is that the reason? So if you see here, when we stratify the study, okay, according to potential confounder, in this case occupation could be the confounder, right? So when we stratify the analysis and we see that male gender and disease malaria in outdoors 1.06, right, in indoors 1.0. So not much different, okay, 1.06 and 1 similar compared to the crude, which is 1.71. Right, so it can be concluded that occupation is a confounder. Right. Now we can also look at the the stratified analysis can also help us to allow for the assessment of possible presence of interaction. Okay, interaction. In this case, the stratum specific odds ratio are very similar or homogeneous, so indicates no interaction. Okay. But if the interaction but if the stratum specific odds ratio are different, like for example 1.4 and 20, so that might be reflections of true interaction. Okay, compared to 1.4 and 2.0. In this example, this is very near, so this in this example it is quite clear cut, but in other situations you might have to think whether the differences in the stratum specific odds ratio are big or not. Right. So of course you need to consider whether the interaction is quantitatively significant or qualitatively significant, right? So between this one and this one, now you have to give reasons, to have strong opinions on that, and then it should be consistent with the pre-established hypothesis, right? Especially with biological plausibility. So now in table 7.2, right? So in this example, oral contraceptive in association with MI among women. So again, do the analysis for the whole sample, and then think about what is the confounder. So it could be age as the confounder. If you think age is confounder, then stratify the analysis by age. So in this example, they stratify into age 25 to 29, 30 to 34, 35 to 39, 40 to 44, 45 to 49, and you look at the odds ratio. Okay, and this is the crude, and this is the stratified odds ratio. Again, in table 7.2, a case control study, oral contraceptive as possible risk factor for MI among women. So if you look at the crude odds ratio, 70% higher than the odds of those who did not use oral contraceptive. So, but if you stratify, all but one of the strata had estimated odds ratio further away from 1.0. So this confirmed the expectations of negative confounding. That is, age driving the estimated crude association toward the null. Okay. So you see here the adjusted odds ratio was found to be 3.97, more than twice the crude estimate. Right. That is stratification. Of course, you need to read the chapter and look at the example 7.1, table 7.1 and table 7.2, and try to understand how the interpretation of the crude odds ratio and the stratified odds ratio can give you idea of the confounding or the interaction. Next, for adjustment, you need further assumptions, because now you are doing statistical analysis, and you need to know that all adjustment techniques assume some kind of statistical model, right? Statistical model can be a simple one. Okay, for example, direct and indirect. Or more mathematically complex model for multivariate adjustment, for example, in regression methods. So now we look at the adjustment methods based on stratification. We have direct adjustment and we have indirect adjustment. So if you look at table 7.3, okay, this one, this is a direct adjustment. So I hope what you can do is to study table 7.3, and you should be able to calculate the crude and adjusted measure of association. So in table 7.3, it outlines the procedure to compare incidence rate between two groups, A and B, which is exposed and non-exposed, and then stratify by the suspected confounding, right? So and for each stratum of the suspected confounding variable, you calculate the incidence, then you choose a standard population with a specific number of individuals, right, in column 8. Then you calculate the expected number of cases in each stratum of the standard population, right? Alright, so you get column 9, and in column 10, right, which is the number in the equivalent standard population stratum. Then you got the overall sums of expected cases in the standard population. Right. So this is the standard population. So you have expected cases using incidence of A and expected cases using incidence of B, right? So this is the adjusted incidence, right? Next is indirect adjustment. Traditionally used for age adjustment of mortality and morbidity data. Particularly popular in the field of occupational epidemiology. So you have the expected number of events, death, in a study group. Okay, for example, occupational cohort. And then you apply the reference rate to the number of individual in each stratum of the study group. So next is for each study group, you get the ratio of the total number of observed event to the number of expected event, right? So what you get is something called as standardized mortality ratio, right? Or in morbidity data, it is called as standardized incidence ratio or standardized prevalence ratio. So table 7.7, which is indirect adjustment. So this is the suspected confounding variable, for example, like age. So you categorize the age here. And then in study population, you have the number, then you have the observed death. And then this is the rate of the reference population, okay? The rate of the reference population from this population, okay? not from this, not from this. Then you get the expected death. Okay, this is the number of column 1, column 2, 3, 4, 5. All right. So you get these values, the the observed death, and this is the expected death ratio between the two, and you get standardized mortality ratio. Next, you can do Mental-Hansel method of estimating the adjustment of association, or Mental-Hansel method for estimating an adjusted measure of association. So for example, in table 7.9 you have cases and controls, and you got exposed and non-exposed. All right. We come back to table 7.1, crude analysis, stratified by occupation because we thought that occupation is the confounder. Confounder, is it occupation? Occupation, outdoor or indoor. All right. And so this is the crude odds ratio, this is the stratified odds ratio, right? But now what we are going to do is we are going to calculate the odds ratio for Mental-Hansel. All right. So this is the formula. All right. You don't have to memorize. I think we will give you we will provide formula in exam, right? So in this case, if you look at the odds ratio Mental-Hansel, it lies between the stratum specific estimate, right? 1.00 to 1.06, and the odds ratio Mental-Hansel lies between the two numbers. This is the example for table 7.2, table 7.2, stratified analysis, case control study of oral contraceptive and MI in women. So this crude analysis, all cases and control. This is stratified by age because we thought that age is a confounder. So we have how many? 1 stratum, 2 stratum, 3 stratum, 4 stratum, and 5 stratum. We got 5 strata. Okay, 5 strata, and we calculate odds ratio here for the stratified analysis. But for Mental-Hansel, the formula is a bit more complicated, and then this is the odds ratio for Mental-Hansel. The assumption is that the adjusted odds ratio is that there is homogeneity of effects across the categories, right? In other words, it is assumed that there is no multiplicative interaction between the exposure and the stratifying variable. Okay, the odds ratio for the stratum should be almost similar, right, to 3.97, right? but in this case it is not, right? So this suggests interaction. Okay, because if you look here for 25 to 34 years old, it is the odds ratio for mental hazard for that stratum is 8.3, and odds ratio for age 35 to 49 years old, it is 2.7. So it indicates interaction, because the odds ratios between stratum are different. So limitations of stratification. Okay, we have shown you that you can do stratification. Okay, and then we show you about adjustment, direct and indirect, and we also showed you the mental Hansel stratification. But there are limitations for these methods. Although they can be used to adjust for several covariates simultaneously, adjustment can happen between one independent variable and an outcome at one time. All right. So, for example, association of oral contraceptive with MI while controlling for age and educational level, it will be much more complicated. Okay, it will be necessary to create a 2x2 table for oral contraceptives vis-a-vis MI for each stratum defined by combining age group and educational level. So it will be, very complicated. Okay. It is. I don't think it is complicated. I think it is troublesome. It is cumbersome. It is not efficient to do that. All right. And these methods allow adjustment for categorical covariates, and for gender, for example, if you got continuous covariates, then you need to categorize them, right? And again, if you want to stratify more than one continuous covariates, then it will be cumbersome, it will be inefficient. And the last one, data becomes sparse, because if you create too many strata, then the cell size will be small for some of the cells. Right? Not many numbers in the cell. Okay. So what you can do is you can do multiple regression techniques for adjustment. So you have learned this one in your MPH course program. So you have linear regression, logistic regressions, Cox proportional hazard regressions, Poisson regression. All right. So this is the model, the statistical model, right? This is the Cox, right? So you have learned that in your class in MPH program, and I think I will not spend too much time for that matter, right? But you need to read this chapter and understand briefly linear regression, logistic regression, Cox and Poisson, from the perspective of epidemiology, right? And of course, what you are doing in these models is to estimate the regression parameters, one of the objectives. So what does it mean by this parameter beta, right? Log odds, log hazard, log rate, okay? There are other alternative approaches for the control of confounding, right? One is the instrumental variable method. This approach uses directed acyclic graphical techniques, or in short we call it DAG. So to identify the existence of a variable, the instruments that is causally related to the exposure of interest, but it is not related to the outcome other than through exposure. So under such circumstances, when we study the relations between the instrument and the outcome, or more specifically by regressing the exposure on the instrument, and then this step number 1. Step number 2 is regressing the outcome on the predicted value of the exposure, right? One can make causal inferences with regard to the relation between the exposure and the outcome that are not affected by the presence of unmeasured confounding. I know it is hard, so it is brilliant if you can go back to the text and read more and understand it. You must make sure that the instrumental variable be causally associated with the exposure. It affects the outcome only through the exposure, and it is not associated with any confounders, known or unknown, right? These are the three conditions that you must meet before you do instrumental variable technique, right? So for example, in figure 7.12, this is the exposure, okay, or the independent variable. This is the outcome or dependent variable, and you have one more, which is the instrumental variable, okay, and this is the confounders, okay, this is the confounders. So by using the instrumental variable, you don't have to think about the confounders here, okay, right? So this technique is interesting, all right. So for example, in figure 7.13, example of the application of instrumental variable analysis when studying the relation between childhood schooling, all right, and memory of old age, okay. So this is independent variable, this is dependent variable, and these are the confounders, all right. So the next question, how can we remove the effect of confounders in the analysis? So what the figure tells you here is that by studying the relation between previous existence of compulsory minimum schooling, state laws and epidemiological data on memory of older people, and inference can be made with regard to the relation between schooling and cognitive function. So this is the instrumental variable, and you must remember must fulfill 3 conditions, right? And then you do regression 1 here and then regression 1 here. Okay, there's 2 regressions done, right? So the correct analysis, sorry for that. The correct analysis involves 2-step approach. Number 1, a regression of the instrument on the exposure. Okay, instrument to the exposure. All right, and then sorry, this is wrong. So number 2 is regression of the predicted years of schooling, this one, on the outcome. So the regression coefficient estimated for the predicted years of schooling thus represent an unbiased estimate of the association between schooling and memory in old age, right? Next is propensity scores. Propensity scores is the predicted probability or propensity of exposure in particular individual based on a set of relevant characteristics. Okay. The idea is to try to mimic randomization by making the exposed and the unexposed group as comparable as possible with respect to relevant confounding variable. So also involve 2 steps. Number 1, exposure variable is modeled as the dependent variable in multiple regression. Okay, this is the exposure variable or the primary variable or the variable of interest. Okay, for example, in this in the example given, the authors use the exposure variable is coded as either treated or not treated, and then the exposure variable becomes the dependent variable. Okay, and then predictor covariates are considered as possible confounders of the exposure outcome association. Then the intercept and regression coefficient from this multiple regression can then be used to calculate the predictive probability of exposure as a function of this multivariate sets of possible confounding variable. So these predicted probabilities, okay, this is what we call as propensity scores, can then be applied to generate new data set of mesh exposed and unexposed individual based on propensity scores. It is difficult to visualize this unless you do it, right? Or you use a data set and practice this. In Stata, there is a program for this, right? And in R, there is a package called Mesh It. Okay, Mesh It package that you can practice propensity scores. That is incomplete adjustment, residual confounding. This happens if the categories of the confounding variable are not defined properly. Okay, for example, when attempting to adjust for a continuous variable using categories that are too broad, right? So that will create residual confounding. The next one is variable used for adjustment is an imperfect surrogate of the condition or characteristic the investigator wishes to adjust. Okay, so that's why it is important to consider the issues of construct validity, okay, for during adjustment. Okay. Other important confounders are not included in the model, so that can give rise to residual confounding. Okay, so if some of the confounding variables are left out of the model, so the adjusted estimate will obviously still be confounded, or confounding variables are misclassified. Okay, so in this example, this is perhaps what we can consider as, under adjustment. But we have a situation where there is problem of over adjustment, over matching, okay, where when adjustment is carried out for a variable that is either in the causal pathway or so strongly related to either the exposure or the outcome that their true relationship is distorted. Okay, so you adjust too much, all right, your model. For example, adjustment for hypertension, when you examine the association between overweight and hemorrhagic stroke. Okay, overweight and hemorrhagic stroke. If you adjust hypertension here, right, it will make the relationship between obesity and stroke less pronounced, okay, less visible. Okay, over adjustment may also occur when adjusting for variable closely related to the exposure of interest, right? For example, here is what? Adjustment for residents when studying the relationship of air pollution to respiratory diseases. Other examples, you include BMI, weight, waist-hip ratio in the same regression analysis. That is also considered as over adjustment.